So next, let's do an example of how to use the friction force. So in this problem that's on the screen now, we basically have a wall here. I'm just going to use this to represent the wall. And then we have a block being held up against the wall by a force that's kind of like this at an angle upwards. And you can see the block doesn't slide up or down on the wall. So what must be the coefficient of friction in order for this to work, in order for the block not to slide as it's being held against the wall? Okay. So step one, we go to the basic F equals ma procedure, and step one is draw a free body diagram. As usual, that's going to be your basic starting point. So I've got my wall here. I've got my book here. It says the book is being pressed against the wall at an angle 10 degrees above the horizontal. So that's going to be a vector like this. Let's get the horizontal direction in there. So this is a 25 Newton force, it says, at a 10-degree angle above the horizontal. We also have, we know that the book is 1 kilogram, so there's a gravitational force pushing the book down. So that's going to be mg. And lastly, we have the friction force. So which way is the friction force going to point? I guess, you know, theoretically in this problem, you don't exactly know whether the friction force is going to be up or down. If this 25 Newton force would cause the object to slide up the wall, then friction would be going down. If this 25 Newton force, you know, is not enough to oppose gravity and it would actually want to slide down the wall, then the friction would be up. I think in this case, the friction is going to be up because it's only a 10-degree angle. So there's not going to be a very large component to that force, a very large vertical component. So I think the gravitational force is going to be larger. We could double check that if you want, but I think the gravitational force is going to be larger, and I'm going to say that the friction goes upwards. And if that's wrong, I'll end up getting a negative friction force or something, and the math will kind of correct me. Then I also have one more force to include. Because the book is in contact with the wall, there's also going to be a normal force of contact. You can't have a friction force without a normal force. The normal force is going to be in that direction, perpendicular to the surface and preventing them from passing through each other. So then I've got a total of 4 forces there. And I think that's everything. So now I've got my free body diagram. Step 2, make sure I have the components of all these forces. There's only one force here that needs to be broken into its component. Well, let's just be extra careful about this and make sure. Okay, so let me make a little chart here. So we've got friction force, we've got normal force, we've got gravitational force, and we've got the 25 Newton force. Okay, friction force is in the positive y direction. I'm not going to worry about plugging anything in yet. I'm just going to say whatever, however you calculate the friction force, it's in the positive y direction. Normal force is in the positive x direction. Mg force, that's the tough one. That one has a component in negative x and a component in positive y. So it's going to be 25 cosine of 10 in the x direction. And over here, it's going to be 25 sine of 10 in the y direction. Except I wrote that in the wrong place. Silly me. That is the 25 Newton force, of course. I don't know why I wrote that as gravity. Now gravity is in the negative y direction. So that's going to be minus, the mass here is 1 kg, and g is 9.8. Okay. So there's all my force components. The rest are 0. The blank ones are 0. And the acceleration here is going to be 0 because it's implied by the question here that the book is held stationary. Actually, it says it explicitly right there, that the book is held stationary. There's no motion, so there's no acceleration. So then my two equations are going to be in the x direction. I'm going to get normal force minus 25 cosine 10 equals 0. I'm just dropping units at this point. And in the y direction, I'm going to have friction force plus 25 sine of 10 minus 9.8 equals 0. So those are my two F equals ma equations. Now, those can be solved very easily. So let me go ahead and do that before I really think about how exactly I want to process the friction force. Let's see what I'm working with. I have here normal force is going to be equal to 25 cosine 10. So that is cosine of 10 times 25, 24.6 Newton. And over here, the value of the friction force is going to be 9.8 minus 25 sine of 10. And I got that as positive 5.46. By the way, since I got a positive friction force there, I was right about the fact that the friction force does in fact point up. If I had gotten a negative friction force there, that would have told me something is wrong, and I must have put the vector in the wrong direction because the magnitude can't be negative. Okay, so anyways, now what? Now how do I actually answer the question? So I've obtained the normal force, I've obtained the friction force. Now I need to actually think about the three different cases of how to handle friction and which one I'm in here. So the book is being held stationary. So clearly this is a static friction case. And the question is, what must be the coefficient of friction in order to hold the book in that case? So in other words, what must be the coefficient of friction for this situation to just barely be possible? Because that's the crossover between whether it's going to be stationary and whether it's not going to be stationary. So in this case, I'm going to want to use the crossover borderline formula where I have friction force equals mu sub s times the normal force. And again, in general, the static friction force is not equal to mu sub s times the normal force. But I'm going to assume that it is here, because if you prefer to do this a little bit more pedantically, we could say what I'm really doing is I know that the friction force has to be less than or equal to mu sub s times the normal force. And we're really putting a bound on the coefficient of static friction. So if I plug in my numbers here, I have 5.46 is less than or equal to mu sub s times 24.6. So 5.46 divided by 24.6 is 0.22. So the coefficient of static friction has to be greater than or equal to 0.22 in order for this situation to work out. And by the way, that's not a typo of dropping units there. The coefficient of friction actually does not have any units. It's just a number. It's just a pure number. And generally it's like between 0 and 1. So that's a pretty normal, typical value for a coefficient of friction. So there's what we got in that case. You'll notice a few things that I want to highlight here. Number one, I was able to solve for the normal force and the friction force without using any new formulas at all. All I used was F equals ma, other than getting the directions of the different forces. I didn't use any formulas for the normal force. I didn't use any formulas for the friction force in order to calculate them because it was a static friction case. Normal force never has a formula to plug in. Friction force doesn't have a formula to plug in if it's a static friction case. I only used the formula over here to actually answer what the question was asking. But the most important take-home message is when you're learning about these new forces, don't get caught up in the specifics of the new things that you're learning. It's all in the context of the main problem-solving strategy that you learned at the beginning of the F equals ma procedure. Draw the free body diagram, break the forces into components, write down the F equals ma equations. And that's how we're going to solve all these problems.